Lesson 4, Solving Exponential Equations. Before we solve some exponential equations like these here and that one there, I want you to practice changing bases of powers. That's going to be an important skill to be able to do while we're solving some exponential equations later in the lesson. So let's do this example here. Example 1 says, express each of the following in terms of a power with a base of 2. So let's change all of these to base 2 powers. So part A, to rewrite 8, that's easy. 8 is just 2 cubed. Part B, if I want to rewrite that as a base 2 power, well, let me just start with the 4. I could rewrite 4 as 2 squared. So I have 2 squared cubed. And then if you have a power of a power, we multiply the exponents. So this equals 2 to the 2 times 3, which is 6. Part C, I'll have to do some simplifying. The square root of 16, well, it might help if I just rewrite that as 4 right off the bat. And the 5th root of 32 is just 2, so that actually helps. So now I just have 2 cubed. And 4 I could rewrite as 2 squared, so I have 2 squared times 2 cubed. When multiplying powers with the same base, we keep the base and add the exponents. 2 plus 3 is 5. So I was able to rewrite all 3 of those expressions as base 2 powers. Let's do one that's a little bit more difficult. Part D, we want to rewrite 12 as a base 2 power. Well, 2 cubed is 8 and 2 to the 4 is 16. So how am I going to put an exponent on 2 and get 12? It's not going to be an integer exponent, but there is an exponent I can put on it. And if I'm looking for what exponent can I put on 2 to get 12, well, a logarithmic function can figure that out for me. So let me call the exponent x, and if I want to figure out the value of the exponent that goes on 2 to make it equal 12, the logarithmic function, log base 2 of 12, would tell me what that is. And let me just show you how that works. So if I did log base 2 of 12, the answer is the exponent that if put on 2, I get 12. But I don't want to write the approximate version of the answer. I don't want to have to round this. So what I'm going to do is just leave it in exact form. Leave it as log base 2 of 12. So put log base 2 of 12 as the exponent on 2, and it makes it equal 12. So I could rewrite 12 as a base 2 power if I do 2 to the power of log base 2 of 12. If you understand logarithms, hopefully this makes sense to you. This exponent right here, log base 2 of 12, the answer to that is the exponent that goes on 2 to get 12. So what happens if we put it as the exponent on 2? Well, what happens is exactly what it says will happen. We get 12. And we could write ourselves a little rule for this. If we have a to the log base a of b, that's just equal to b. So this example was just here to show you that any positive number can be expressed as a power of any other positive number. All right, example 2, we're actually going to solve some exponential equations now. And they're exponential equations because our variable is in the exponent. Now, to solve exponential equations, the easiest thing to do is to try and make your equation look like this. Try and make your equation so that you have power equals power, where the bases of those powers are the exact same thing. If we can get it into that format, where the bases of the powers are equal, then I would know that the exponents would also have to be equal for the equation to be true. So if we have x to the a equals x to the b, then we know that a has to equal b. That's the only way the equation could be true. So for part A and B, that's what we're going to try and do. We're going to try and get it into this format. So on the left side of the equation, I have a base 4 power, and on the right side, I have a base 64 power. If I could rewrite those with the same base, then this equation would be easy to solve. Well, 64, I could actually rewrite as a base 4 power. 64 is 4 cubed. So I'll change the 64 to 4 cubed. And now I'll use my exponent rule that tells me if I have an exponent on top of an exponent, I multiply them. So 3 times x, I would just write that as 3x. And now notice I have power equals power, where the bases are equal to each other. When that happens, we know that the only way the equation could be true is if the exponents were also equal to each other. So we set the exponents equal to each other and solve. So I'll subtract the x to the other side and then divide both sides by 2. I get x equals 5 over 2, or 2.5, however you want to write it. And don't forget, when solving an equation, you can check your answer. plug it back into the original, make sure it makes left side equal right side. There we go. I've just verified we found the correct answer. Part B, let's try the same strategy. Let's try and make this power equal power where the bases of the power are the same. Well, I can't easily rewrite 8 as a base 4 power, but I should notice that 4 and 8, I could write both of those as base 2 powers. 4, I could write that as 2 squared, and 8, I could write that as 2 cubed. And now use my exponent rules. So I would have on the left side of the equation 2 to the 4x, and on the right side, I have to multiply this x minus 3 by 3. So don't forget to multiply the x and the negative 3 by 3, right? We're doing those multiplications. So I would have 2 to the power of 3x minus 9. And now that I have power equals power, where the bases of the power are equal to each other, I can just set the exponents equal to each other and solve. Subtract the 3x over, and I get x equals negative 9. And don't forget to actually check and make sure that's the correct answer. Plug it back into the original, make sure left side equals right side. There we go, I verified it's the right answer. Now part A and B were relatively easy because we were able to rewrite those powers with the same base pretty easily. But what if we can't do that? Look at example 3, part A. I have a power of 4 and a power of 3. It wouldn't be easy to rewrite those powers to have the same base. Like I could, I suppose, write 4 as a base 3 power. It would be 3 to the log base 3 of 4, and then that's to the exponent of 2x minus 1. But I don't think this is going to make the equation any easier to solve. So let's not do that method. Let's instead do what it says here. It's probably easier if we take log of both sides, use the power law of logarithms to remove the variable from the exponent, and then try and isolate the variable. Let me show you how we do that. So like I said, not easy to rewrite 4 and 3 as powers with the same base. So what I recommend you do is take log of both sides, and after we've done that, we use the power law of logarithms, which tells us we're allowed to take the exponent of the argument and rewrite it as the coefficient of the log. This is a really useful rule because it allows us to get our variable out of the exponent, and then it's going to be a lot easier to isolate. So I've taken that 2x minus 1, it becomes the coefficient of the log. To make sure the whole 2x minus 1 is the coefficient, I need to make sure I put it in brackets. So 2x minus 1 log of 4 equals x plus 2 times the log of 3. And now my goal is to isolate x. In order to do that, I'm going to first have to expand both sides of this equation. So this log 4 is just a number. It needs to be multiplied by the 2x and the negative 1. So I've got to do 2x times log 4 and also negative 1 times log 4. And same thing on this side, I have to do x times log 3 and 2 times log 3. So that would give me, on the left side, 2x log 4 minus 1 log 4 equals x log 3 plus 2 log 3. Now it's fully expanded. I have 4 terms. 2 of those 4 terms have a variable. That term and that term, we call those the variable terms. Since I want to isolate the variable, a good strategy to use is to get all the variable terms to one side of the equation, and then get the constant terms, log 4 and 2 log 3, to the other side of the equation. So I'll bring the variable terms to the left, so leave 2x log 4 where it is, and subtract x log 3 to the left. On the right, I have 2 log 3, and I'll bring over this negative log 4 by adding it, so plus log of 4. And on the left side of the equation, notice both terms have an x, so I can common factor an x from both terms. So if I divide both of those terms on the left by x, I would have 2 log 4 minus log 3 equals 2 log 3 plus log 4. And then a lot of these logarithmic expressions I could simplify using my product, quotient, and power rules. You don't have to. I mean, we could now just divide both sides of the equation by this, and then that would isolate x. We could type it in our calculator and get our approximate answer. But I'm going to simplify some stuff first, get it as simple as possible before I type it in. So for example, this 2 log 4, well, that 2 could be moved up as the exponent on 4. So that's really just a log 16. So I've got x log 16 minus log 3. And same thing on the right, I could take this coefficient of 2, put it as the exponent on the argument. So that would give me log of 3 squared, which is 9. So log of 9 plus log of 4. And now I'm going to use my quotient and product rules. On the left side, 2 logs being subtracted where the logs have the same base, I could write that as a single log with the arguments being divided. And on the right, 2 logs being added where the logs have the same base, write it as a single log with the arguments being multiplied. 9 times 4, 36. And now I just need to divide this log of 16 over 3 to the right. So x equals log of 36 divided by log of 16 over 3. And we could just type that in to get our approximate answer. But I could also rewrite those 2 logs as a single log if I use the change of base formula. I could rewrite those 2 as log base 16 over 3 of 36. And that would be an exact answer. If I want an approximate answer, I'll type that in. And my approximate answer would be about 2.14. All right, part B. It's a very similar type of equation. We're going to use the exact same strategy. It's power equals power, where those powers would not be easy to rewrite with the same base. We can't rewrite 2 and 3 with the same base easily, so what we do instead is take the log of both sides and use our power rule to get the variable out of the exponent and then try and isolate the variable. Pause the video now and try this one on your own. Follow the exact same strategy as the last one and see if you're able to get the simplified exact answer and also the approximate answer. So pause now and try. All right, now watch my solution and compare yours to mine. Okay, hopefully you're able to get the right answer. If not, make sure you correct your solution and follow the steps that I outlined here. Let's move on to the most difficult exponential equation we're going to solve in this unit. And with this one, we're going to uncover a hidden quadratic and be able to solve it the way we solve quadratics. So the equation starts off looking like this. 2 to the x minus 2 to the negative x equals 4. To solve this one, what we're actually going to do, and I know this seems like a little bit of an arbitrary step this first time we're doing it, but I'm going to multiply both sides of this equation by 2 to the x. And I'm allowed to do that as long as I do it to both sides. So I have 2 to the x times 2 to the x minus 2 to the negative x equals 4 times 2 to the x. So I multiply both sides by 2 to the x. And now on the left side, I'm going to distribute my 2 to the x to both terms in the binomial. And when I do that, I'm going to need some exponent rules. 2 to the x times 2 to the x. Powers being multiplied with the same base, I can write as a single power with the exponents being added. X plus x, 2x. Minus 2 to the x times 2 to the negative x. Same thing, write those as a single power by adding the exponents. X plus negative x is 0. And 2 to the 0, well, that's just 1. So I'm actually going to move all the terms to the left side. So I have 2 to the 2x minus 4 times 2 to the x minus 1 equals 0. And I specifically wrote it in this format because notice now I have a hidden quadratic. And it may help if I rewrite this 2 to the 2x as a 2 to the x squared. So I have 2 to the x squared minus 4 times 2 to the x minus 1 equals 0. If I use a let statement, let's say let k equal 2 to the x, that'll probably make it obvious to you that we have a hidden quadratic. So replace all the 2 to the x's with a k, and I would have k squared minus 4k minus 1 equals 0. And you know how to solve this for k. We would try and solve it by factoring. Is there anything as a product of -1 is sum of -4? Well, no. So that just means there are no rational answers to this. We'll use quadratic formula and see if we can get some irrational answers. So we'll do k equals -b, so 4 plus or minus the square root of b squared, so -4 squared minus 4 times a times c, all over 2 times my a value. And then we'll simplify this as much as we can. K equals 4 plus or minus. Underneath the square root, I have 16 plus 4, that's 20, so root 20 over 2. And this could be simplified. I could split root 20 into root 4, root 5, which means 2 root 5. And I could simplify this by, in the numerator, common factoring out a 2. And simplifying by doing 2 divided by 2 is 1, so those cancel. So k equals 2 plus root 5 and 2 minus root 5. And if in the original question we were trying to solve for k, we would be done. But actually, we're trying to solve for x. Oh, and we know that each k is actually a 2 to the x. That's why over here, I've said, okay, well now we have to substitute our answers for k back into that let statement, where we know k is equal to 2 to the x, right? K is equal to 2 to the x. So we have two cases where k is 2 plus root 5, and k is equal to 2 minus root 5. And now we solve both of these exponential equations for x. So in case 1, we're trying to find the exponent that goes on 2 to get 2 plus root 5. We can use a logarithmic expression to find us that. So convert this to logarithmic form. It would be x equals log base 2 of 2 plus root 5. And let me evaluate that. And I get 2.08 approximately. It's about 2.08. There's one solution. And then if we try and solve this one, we're wondering what exponent goes on 2 to get 2 minus root 5. There actually is no answer for that, but just to show you, if we converted this to logarithmic form, I'd have log base 2 of 2 minus root 5. And if you tried to evaluate that on your calculator, it's going to tell you error. Let me just show you. It says error, no real answers. And why is that? It's because of the argument, the 2 minus root 5. What's the approximate value of 2 minus root 5? It's negative 0.2. And remember, logarithmic functions are only defined when the argument is bigger than 0. So if the argument is less than 0, there's no solutions. So I'll make a note of that. 2 minus root 5 less than 0. Therefore, no solution. So our only answer to the original equation is this. X is about 2.08. And don't forget that you can actually plug that back into the original, make sure it works. And when I plug it back into the original, I'll use the exact value. So 2 to that value minus 2 to the power of negative that value should be equal to 4. And it is. We found the correct answer. Okay, that's it for solving exponential equations. Make sure you try your practice questions for this section. In order to get good at solving exponential equations, you have to practice a lot.